Welcome everybody to episode 6 on our programming subseries. We're going to be talking about the float/double primitive types. So these are similar, but they're not exactly the same. The double is just a lot more precise. So these both represent fractions, whereas our integer represented whole numbers. And the thing with the float and double types are we have to use a standard to represent them in binary because we have this decimal place, whereas in the integer we just had a number so we could convert it straight to binary. Now we have a decimal place, so there's a problem. So we use what's known as the IEEE 754 standard, also known as the IEEE standard, and this is just a standard that defines how we're going to represent floating point numbers in binary. So there are a few steps to actually converting the decimal number into a binary number. So we convert the left side of the decimal into binary, so this side. Then we convert the right side into binary. And then we do what's called normalizing. So I have an example here. Say after we have our binary numbers of the left and right, so that's just the left hand side and the right hand side, we do this thing called normalizing. So that's just moving the decimal place so that there's only one number to the left of it. So in this case we'd move it 2 places to the left, so we get 1.01011, and then we multiply that by 2 to the power of 2. And you can think about it this way: this power right here, if it's positive, that means we're moving the decimal back to the right 2 places. If it's a negative, we move it to the left 2 places. But it's positive here and it's 2, so we move it to the right 2 places to get our original number 101.011. So that's just what's known as scientific notation, and that's what's known as normalizing a number. And then we use the actual standard, the IEEE standard, to represent that binary number that we got. So you can see here we have a power, we have a fraction part, and then this number, since binary uses only zeros and ones and the 1 is the most significant bit always, we're going to basically be implying this 1 here. There's always going to be a 1 here, so we don't really have to worry about it. So we have 3 parts in both the float and double types using the IE standard. We have a sign bit, which just says whether the number is positive or negative. 0 is positive, 1 is negative. Then we have the exponent bit, and the exponents for each of the float and double use what's known as a bias. And the bias makes sure that we can represent negative and positive exponents. So the bias for float is 127. Because we use 8 bits, and if we just do a quick calculation here, 2 to the 8th is 256, so we have a negative and positive side, so we divide that by 2, so that gets us 128, and remember we're starting from 0, so it would be minus 1, so 127. That's where that bias number comes from. You can do that with the double 2, which uses 11 bits. But anyway, this exponent represents this exponent right here in our normalized number. And all we would do to actually get the actual number we're going to use in the binary is just add that bias to whatever number we already have. So 2 plus 127 is 129, so we would just convert 129 into binary and throw it into this exponent section. And then the mantissa, it's called mantissa, that's just the formal name for it, but we can think of this as the fraction part of the binary number. So this is just everything to the right of it, of the normalized number, so we would just copy and paste all of this into the mantissa. And then it's the same for the double. I explained the float, but it's the same thing for the double, just we use different sizes. So you can see our float uses 8 bits for the exponent and 23 bits for the fraction part, where the double uses 11 bits for the exponent and 52 bits for the fraction. That's why the double is a lot more precise than the floating point or the float. One thing to know about the difference between float and double conversions is that when we're converting to a float type, it's called single precision conversion, and when we're converting to a double, it's called double precision conversion. Alright, we have some practice here. So we're converting 3.0125 to a floating point using the IEEE standard. So our first step is to convert the left side of the decimal to binary, so that's just 1 1, and then we convert the right side to binary, and this is a little different because it's less than 1. When we have numbers that are greater than 1, we use that technique of dividing by 2 and storing the remainder. With numbers less than 1, we do the opposite. We multiply by 2, and then we keep whatever's on the left hand side of the decimal. So 0.0125 times 2 is 0.0250, and there's a 0 here, so we store that. And then we do the same thing until we reach a 1 on the left hand side, so you can see times 2, 0.05, and we keep doing that until we get to 0.8. So 0.8 times 2 is 1.6, so we store the left hand side, which is 1, and then we just create a 0 here, so we just drop the 1 and put a 0 there. So 0.6 times 2 is 1.2, keep the 1, and then we're back to 0.2, and you can see we had a 0.2 here, so the pattern is just going to repeat. So this pattern of 0011 is just gonna repeat forever. So we have 0000, 0011, 0011 as our 0.0125. So now we have the left hand side and right hand side in binary 11.00, so on and so forth. Now we need to normalize the number, so that's step 3. We just move the decimal 1 place to the left, and that gets us 1.1, so on and so forth, times 2 to the first. And then we have to use that bias number to get our actual exponent, so 1 plus 127, because we're converting to a float, not a double. So 1 plus 127 is equal to 128 in decimal, and then we convert the 128 to binary, which is 10000000. Alright, step 4 here is to actually use the standard. So you can see we have our sine, exponent, and mantissa sections. So our sine is going to be 0 because 0 is positive in this standard, and we have a positive number. And then the exponent is just that number that we use the bias to create. So it's 10000000. And then the mantissa is literally just a copy and paste of the right hand section. And we have 23 bits, and remember how I said this is a repeating pattern, 0011, so that's going to go on forever. But we only have a certain amount of bits, so we can only use 23 bits to represent it. So that's where this number comes from, and this is using the IEEE standard. Okay, so that's an example of converting to a float from decimal, and it's really the same thing as a double, so we're not going to do an example on that. Plus it would be quite a bit lengthier because we're using 52 bits and 11 bits. Just know that the bias for float is 127 and the bias for double is 123. So when we're converting our normalized exponent, you have to use those numbers depending on what you're converting to. Alright, let's talk about the ranges a little bit. So we're talking about the float and double ranges. The double, as I've mentioned, is a lot more precise. So it can represent 15 digits in the decimal portion of the number, where the float can only represent 6. So the float has a range of 3.4 times 10 to the negative 38th, all the way to the positive version of that. And then the double has the 1.7 times 10 to the negative 308, all the way to the positive version. So it's a lot bigger. Let's talk about why these ranges are what they are from a mathematical standpoint. So we're using the standard of having a sine, exponent, and mantissa section. So the sign is just going to be 0, 1, doesn't really matter. So let's talk about the exponent. The maximum exponent we can have is all 1s for the binary, and then mantissa, same thing, all 1s. So we'll talk about the float specifically. So for the exponent, we have 8 bits. So 8 1s in binary is the number 255, and then we subtract the bias number. So for float, the bias number is 127. We've talked about this. So this gets us 128. So our max number, being all 1s, would be 128 in decimal. And in the IEEE standard, this is used to represent infinite numbers or infinities, and then non-numbers. So we have to use 127 as our exponent, as our max exponent. And then remember how I talked about how the 1 in scientific notation is implied because we're using binary. So let's not worry about that. Let's worry about the mantissa though. So our max mantissa would be all 1s. So 23 1s, because floats, or the float type, uses 23 bits for the mantissa. So 23 1s is some massive number, so it's going to be 1 point some massive number, so it's going to be close to 2, so we just round it up to 2. So now we have 2 times 2 to the 127, and this is equal to 3.4028 times 10 to the 38. So that's where this range comes from. And then the double, I'll let you do on your own, but it's the same procedure, just using the different amount of bits for each section.